Hello everybody and welcome to today's seminar. Today's seminar is instrumentation monitoring for the Ituango Dam. So the Ituango Dam is the most important hydroelectric power project in Colombia. The project consists of 225 meters high air core rockfill dam with a capacity of 20 million cubic meters water and a 77 kilometers length reservoir and an underground power station of 2,400 megawatts of installed capacity. The power plant was located in the rock mass of the right bank, comprised the main cavern of the mechanical room that hosts 8 units of 300 megawatts of nominal power each, with Francis-type turbines. Since the start of the construction for the main work in 2013, geotechnical monitoring has been carried out to follow the stability of the excavation of the caverns, spillway, diversion tunnel, among others. In 2018, in order to obtain timely information about the stability of the main work, a Technical Monitoring Center, TMC, was created for continuous monitoring of seismological, hydraulic, geodetic, interferometric, and geotechnical variables. Currently, 4 of the 8 generation units are fully operational, and the civil work is 92%. The TMC continues to actively participate in the development of the process, centralizing, automatizing, and analyzing all information of interest for the engineers with the aim to transmitting a safety message to the communities downstream the river and other stakeholders. For this presentation, we have 2 engineers with us. The first engineer is Nestor Jurado Betancur. Actually, the second one is not an engineer. He is a geologist, which is Juan Masso Martinez. Nestor is a civil engineer who graduated from the University of Antioquia in Colombia, has an MCS in geotechnical engineering from the Politecnico di Torino in Italy. He has 10 years of experience in consulting on an field assessment for tunneling excavation, slope stability, and foundation. He's currently part of the civil work team for the main company, where he coordinates work teams and executes the construction contracts. Juan is a geologist and graduated from the University of Caldas in Colombia. He has more than 5 years of experience in ground monitoring and work at the Colombia Geological Survey, analyzing seismic data to track volcanic activity and supporting eruptions early warning system. He is currently focused on using remote sensing tools such as INSAR for detailed terrain analysis and geotechnical instrumentation such as inclinometer and piezometers to ensure geotechnical stability during large-scale hydropower and infrastructure projects. So with this, just join me, welcome both.
Thank you very much, Daniel, for the presentation. This is Nestor Jurado here. I'm going to start the presentation. First of all, we will talk a little bit about our company, EPM, which means in Spanish, like Public Enterprises for Medellin. Medellin is one of the most important cities in Colombia. And EPM, or the group EPM, has presence in countries like Mexico, Panama, Guatemala, El Salvador, of course, Colombia, and Chile. And we are a public services company. Our primary functions or our business are generation and commercialization of electric power, transmission and distribution of electric power, distribution and commercialization of natural gas, provision and commercialization of water, management and commercialization of wastewater, management and commercialization of solid waste, and commercialization of new solutions We are more than 16,000 collaborators or workers here in the company, with more than 9 million customers benefit in Latin America, more than 11,000 suppliers and contractors, and more than 35,000 external jobs that we have created with our business. So this is a little bit of our company. And now in the specific topic of the Ituango Dam, this is a very beautiful view of the project. So here we can see the outside main works, and just talk about a little features or the main features of the project. So the power station has an installed capacity of 2,400 megawatts, generated by 8 units. So each unit will generate 300 megawatts for an annual generation of 9,200 gigawatts per hour. This is by far the largest project or hydropower station we have in Colombia. The second one generates approximately 1,200 megawatts. So it's kind of like half of the installed capacity we have here. About the reservoir, we have a reservoir of 77 kilometers long, which has a capacity of 970 million cubic meters. The dam is an air core rockfill dam, has a height of 225 meters, is 1 kilometer long, per 500 meters wide, and has a volume of 20 million cubic meters. And the spillway that you can see in the picture working has a length of 400 meters and a total capacity of 22,000 cubic meters per second. This is by far the capacity that we have normally in the Cauca River, and just this next. So for the location, as you can see, we are in the northwest part of Colombia in a region called Antioquia. This is 170 kilometers from the city of Medellin, the capital city of this region. And as you can see, we are working, or we are generating energy, taking the water from the Cauca River, which is the second largest river in Colombia. So that's why we have we can have that installed capacity for the power generation and those flow capacities. Now we would like to present you the project, but like with a virtual tour. We prepare better than pictures to show you the live or a live view of the cameras we have installed. So we will start by the spillway. Right now the spillway is dry. We are in the dry season. As you know, here in the tropic we don't have the 4 seasons you have. We have only like a dry season and a rainy season. And so right now the channels of the spillway are dry. The gates are closed. As you can see, we have 2 channels. The big one with 3 gates is the right one, and the left one with 1 gate. So we change channels depending on the flow. But right now, all the water that is going into the dam, we are use that water for generation of energy. Now we will see the upstream part, or the upstream phase of the dam. And we can see also the region where the intakes are. There, we can zoom in a little bit. So in that part where you can see the steel roofs, there are the intakes, as we will show you after. There are 8 intakes. So from here we can see also the reservoir and the right margin. Again, please. all the right margin, you can see that huge excavation we performed for the stabilization of the spillway. This is a more than 200 meters high slope we generated just for having the space for the spillway, and it's stabilized by shotcrete and rock bolts. We can also see the part of the reservoir. We can change the camera to see more of the reservoir here. The 77 kilometers long reservoir of the Cauca River. Now we would like to go underground. So first of all, we would like to show you the whole underground complex with this 3D model. And so these are the shallow main works, and now we will turn just to show you where the underground main works are. So you can see all the excavations, all the caverns and the tunnels. Most of them are construction tunnels, just to access to the different fronts and to accelerate the construction of the project. But if we talk about the travel of the water from the intake to the discharge, so you can see the intakes in the upper left here, and also to highlight that each one of the power units has its own conduction tunnels and conduction shafts or pressure shafts for the generation. So the water is coming from the upper conduction tunnels, goes through the vertical shafts to take more energy, and then goes to the powerhouse, which is the largest excavation we have. Is a 400-meter long cavern with 40 meters high, where the 8 units are. On the left or upstream, the powerhouse, there is the transform cavern. And on the right, you can see 2 surge tanks where the water from the units 1 to 4 go after the generation process and in the north part of the project. And in the south part, we have the surge tank number 2, where the water goes after the generation process of the units 5 to 8. Then we have the discharge tunnels, and it's more or less 1.4 kilometers each one of them, just to return the water to the Cauca River after the generation process. Unfortunately, we don't have right now a signal in the camera of the powerhouse, but we can show you a video taken by a drone where you can see the powerhouse. You can see the green circles are the units, the head of the units. As you can see, there are 4 units operating right now. So this is like a hybrid project where we have 4 units completely operational and generating energy since 2022. And this is the south part where we are going to construct the other 4 units for completing the project and the total capacity we will have in this project. Right now, we will continue talking about the geotechnical instrumentation, which is the main topic of this presentation. And we will split this part or this presentation in 2. The first one is going to be the geotechnical or the traditional instrumentation. And then my partner Juan is going to explain the technical monitoring center, which is an innovative way to centralize all the instrumentation and to have a more opportunity of the information by automation of the instrumentation. So talking about the traditional instrumentation, unfortunately our time is short, So we will not go deeper in every instrument, but I would like to mention some of them. Before that, we would like to show you how we manage the instrumentation process through the a model or a format we have in ArcGIS Online. You can see this is like a panoramic view of the project, and we can count, or we can have an inventory of all the instruments. So if we zoom in that window, we can count all the instruments that are in that window. For example, as you see, while we zoom in the dam, we have like we can count in the upper left 441 instruments which are part of the dam, only of the dam. If we zoom out, you can see how that number increases because we're taking into account all the instruments we have. Here we have more than 3,000 instruments in the project, shallow instruments, or in the outside main works, or in the underground works. It's a total of more than 3,000. And we have put this chart to have the inventory and to know what are the state of those instruments. If we, for example, zoom in the instruments of the dam, we can see how many of them are operational in the green bars. And we also have some instruments being checked, and those some instruments are out of service, and some of them are still not installed, which are the blue ones. So like this, we can have a control of the total amount of the instruments. We can have a complete inventory. We can manage better what instruments are pending for installation, what kind of, or what fronts have a lot of instruments, for example, out of service, or what fronts have most of the instruments operational, and have more information to also for the geotechnical engineers and the technical people that works here, and use this like a feedback for the analysis. Okay, going back to the presentation, talking, for example, about the topographic control points or the survey monitoring. We use the total station where we can read information of prisms or targets or concrete blocks installed in the ground to check the X, Y, Z coordinates and check if there is some movements. For example, I would like to highlight these are like standard designs for the concrete blocks we have, and always they are anchored deeper, depends, for example, if it's in the rock or in the soil. So you can have the real measure of or the real displacements of the soil, and not, for example, just placing the concrete block in the surface, because you know there you can, for example, read movements in the organic soil or something very shallow, and not the real movement of this slope. So this is important to highlight how we anchor our monitoring points, just to get the real information about the slope. And with that information, we of course obtain the charts of time displacement. You can see the colored points where we are showing the displacements in time of the different control points. And we have two things to highlight here. For example, the thresholds. You can see the green, the yellow, and red are thresholds that we define. And with that threshold, or with every threshold, we have like an alert protocol if it's necessary. And also we register and we put together here the rainfall registration. in blue, those bars in blue. And we can, for example, analyze here in these charts how the ground or how the slope reacts or responds to the rainfall seasons. You can see how the displacements like trigger after the rainy seasons, and we register more movement, and we register an acceleration of the movement that you can see in the slope of this chart. For example, in the case of the dam construction, we placed control points in the lower layers of the construction or the embankment. So we can register how displacements and settlements increase with the load increase. This is a registration. For example, the first 2 years, you can see how the displacement and the settlements accelerate, and then they start to get a flat, if you can say flat, until they become asymptotic. In this case, for example, touching the threshold green or the threshold number 1, which is like the displacement and the settlements we expected for the dam. In the case, for example, of inclinometers, as you know, inclinometer is like we have a probe, which is like I would like to call that like a little car, which is sliding through the rails. You can see in that figure the rails A, for example, or an axis A, which is normally parallel to the direction of the displacement we expect, and the axis B, which is perpendicular or normal to the direction of the displacements we expect. And then we start to register the cumulative displacement or the displacement measured in every interval here, and then we can see or we can conclude what's the depth of the failure surface, for example, or the total displacement and the direction of the displacement. For example, we can see a real example here. This is a slope we have on the road or the access road to the project, and you can see the registration of the inclinometer. This is a depth versus deformation or displacement chart, and you can see how the curves or how there is a clear distortion at the depth of 60 meters, which means that there is a movement down there, and we are registering in every campaign or every time we go to measure that, we can see how that increases. So we can have a magnitude of the increase in the axis A and the axis B. We can also have the rate of that displacement, and we can have the vector or the direction of this displacement. In this case, because you have the displacements in the axis positive A and positive B, you can see you are in the first quadrant of that displacement. So you can have a pretty much clear idea of what's the depth of the displacements, what's the total magnitude, and what's the direction of the displacement. So this is a very interesting feedback for the geotechnical and the geotechnical engineers we have here in the project, because it is like an interactive conversation between the people in charge of performing these measurements or these charts, and the people who analyzes it and uses it for the design of the support or the stabilization for the slopes or the different works we have here. Unfortunately, we don't have pretty much time for continuing showing you how we manage or analyze the traditional instrumentation. Now I'm going to give the word to my partner Juan David, who is going to explain how we use technology and all the technological means we have available in the world to monitor the project. Okay, so thank you very much for your presentation, Juan David.
Thank you, Daniel, for your presentation, and thanks to everyone who is connected at this time. As it was mentioned at the beginning, my name is Juan David. I am a geologist, and my experience has been based mainly on ground monitoring through conventional instrumentation and also with the use of remote sensing. Today, I have the opportunity to explain to you what the project's technical monitoring center is all about. Basically, this is the TMC. In 2018, EPM made the decision to provide resources to establish a place to centralize the information from geotechnical and hydrometric instrumentation, and also to improve the monitoring of all the project in many ways, including the use of remote sensing, and also to project that huge amount of information in real or almost real time. So as you can see on the screen, we have this innovative solution, this dedicated space. It's a specialized office with a video wall and different workstations, each one in charge of one specific area of knowledge. Daniel has already explained the CCTV station and the geotechnical instrumentation. So I'm going to be focused on these areas. I also have to mention that we are a group of more than 20 people, and with different professions. I mean, geologists, civil engineers, systems engineers, among others. And we work in shifts to provide a 24/7 coverage. So what I'm going to do now is to show you a scene that we built in ArcGIS Online, so you can have a better perception of how our instruments are distributed in the field. And I'm going to alternate that with the PPT, so you can see what those instruments look like in the field and some examples, some real results that we have recorded. So here we have the scene. Give me a minute. Okay, so this is the general view of the project. I know Daniel has already explained the main features and showed you the 3D model in Navisworks, but I think it would be nice if I would give you some key points to keep in mind, just so you can have a better notion of how the project is located and how we refer to it. So, because the Cauca River has almost south-north disposition in this part, it's easy for us to refer this part as the right margin of the project and this part as the left margin of the project. Here we have the base camp. We are presenting from here now. And as you can see, we got to take this road in the right margin to reach the main works. And if we continue by this road, you can get to the municipality of Ituango, which is an important town for us. It's part of the influence area of the project. So I think that's the basics. So we are going to start with the geodesy area, where we work with geospatial and GIS technologies. What you're seeing right now corresponds to the GNSS network that we have installed to monitor displacements in the main work. These devices allows you to acquire signals from different satellite constellations and to determine their position in the X, Y, and Z axis. So here we have the basic configuration of a GNSS station. This is the station that is installed in the spillway. And as you can see, it is a much more robust scheme if you compare it with the traditional GPS that we use every day, right? Inside this metal cabinet, we have a receiver, and also we have all the electrical and the complementary accessories. And at the end, what we obtain is the daily position time series for all the 3 axes. This is the chart for this station, and as you can see, this sector has remained very stable, and we also have a very good precision. We're talking about 2.5 millimeters of precision for the horizontal components, which are these ones. And we're talking about 10 or 15 millimeters of precision for the vertical component. Previously, I mentioned you the importance of this road for us. Particularly in this zone, we have a non-consolidated deposit whose movement increases during times of high precipitation. So what we have done is to install a total robotic station in the right margin of the project, pointing to the left margin, and these points that you see here are the prisms or the targets that we have installed, so we can measure the movement of this area. This station does not need a surveyor. It's totally automatic, and it is taking measurements of those targets every 15 minutes. So here you can see the reference that we use in the project is a Topcon total robotic stations. These are conventional prisms, and here we have something similar to what Daniel was showing you in the part of the topographic points, which is how those points are influenced by the rainy seasons. I have here some examples of the targets, and you can see both the horizontal and the vertical displacement. Finally, for the geodesy area, we have also a satellite monitoring service. 3B Geomatics is a Canadian firm that has been our supplier for more than 3 years. They are in charge of processing INSAR images from Sentinel-1 and ALS-2, and they use complex algorithms to process that images and to deliver this to us. What you are seeing this moment is basically a displacement map with a color scale, but the great advantage with this technique is that you can monitor large areas. For example, here I have data from the tail of the reservoir, and even more than 10 kilometers downstream the dam. And the other advantage is that you can have millions of points with ground displacement data. So what we can see here is a zoom in on a set of points that I selected for the body of the dam, and its statistics associated. For instance, the cumulative displacement for the dam in 2023 was 4 centimeters. And that's good news for us because that's coherent with the topographic points that are installed there. And it also corresponds to our expectations based on the design parameters. So basically that is the geodesy area. I'm going to continue with the interferometry area. I will go quickly here. Basically, in this area, we counted 2 ground radars whose operation is kind of similar to the INSAR satellite monitoring, with the difference that these devices are installed are pointing to specific areas. So we have one radar that is installed in the right margin of the project, pointing to the body of the dam, and we have another radar that is installed in the left margin of the project, and it is pointing to all this sector, all the right margin of the project. What we get from these radars, this is what a radar looks like. This is a reference image, but it's the same device that we have in the project. And I mentioned it was similar to the satellite monitoring service that we have, in the way that we obtain this displacement map. But here we don't talk about points, but we talk about pixels. And those pixels have a very short size, and every pixel has a millimetric precision for the displacement. Of course, you can configure more detailed analysis zones. For example, I have these three zones, and particularly the blue zone has presented an accumulated deformation of almost 80 centimeters in this period of time. But after the corrective measures were applied, the site has remained very stable, as you can see. We're going to continue with the hydrometry area. Here it's very important that you understand that the Cauca River is the second largest affluent of the country. As you can see, it runs through a large part of the Colombian territory. So for us, and at the dam side, it has an average flow of 1,500 cubic meters per second. So for us, it's really important to know the behavior of those flows both upstream and downstream the dam. So what we have done is to install radar flow meters in different parts of the basin. You can see it here, and you can see the name of the station, which is associated with the municipality that is nearby the station, the site of the installation. The basic operation of those radar flow meters consists on calculating the height of the water sheet, and with a calibration curve that is previously set on the device, it can determine the flow in cubic meter per second. So at the end, what we have is this chart with the data of the flow in the different parts of the basin. This is really important for us. For example, the green line is showing us an increase in the flow for La Pintada station. So what we do here is to act preventively, to act creatively, and we share this data to our colleagues of the operations area. And with the time travel of the water that we have calculated, we can know when it's going to be reflected, this increase in the other stations downstream, and when it's going to arrive that volume of water to the project. So our colleagues can manage how to operate, if they can evacuate that flow only for the generation units, or if it is necessary to open the gates of the spillway. In this workstation, we also have data regarding the reservoir level, the turbine flow in each generation unit, the Ituango River, which is close to the dam, and also the spillway gate opening level. So that's basically the hydrometry area. In the area of seismology, we have two seismological networks. The first network is made up of 12 stations installed throughout the area of influence of the project. You can see the points in green. The purpose of this network is to carry out studies of induced seismicity. This means how the seismicity of the zone has evolved before, during, and after the filling of the reservoir. And we also have another network, the second seismological network, which is made up of 8 seismometers that are installed around the main works, and intends to carry out a more focused analysis on different events that may occur during the development of the project. What we are going to obtain, this is the basic components of a seismological station. This is the seismometer. It's a very sensitive instrument, and this is a digitizer, and this is the basic scheme with the electrical and the accessories, the complementary accessories. What we obtain is something like this. This is the real-time visualization of the ground vibrations. Those who work in this area use different parameters, such as the waveform, the frequency, the amplitude, the arrival time, among others, to classify the different recorded signals and associate them with the phenomenon that is occurring. Here are some signals that make up our seismic catalog. We have been able to record everything from tectonic events to issues clearly related with the project activities, such as the flow of water through the spillway or through the caverns, and also the passage of heavy machinery in determined sectors. To finish my presentation, I want to show you this particular case that we managed to record from the seismology area. At the end of 2022, the generation units 1 and 2 were about to start its commercial operation. So a series of tests were carried out in those machines to verify that all the electromechanical components of the turbines were working well. During those tests, we were able to record signals associated with that first spin and with the rotation of those turbines. So as I mentioned before, what we did was to characterize those signals using the waveform that you can see here. You can see the increase, a considerable increase in the energy, and then the return to a level similar to those before the spin of the machine. And we also here have the frequencies associated to those signals. As you can see, the dominant frequency is 20 Hertz, roughly, and then we can observe frequency drop until it reaches the initial levels of energy. And we also did carry out analysis, a more detailed analysis, using a tool called the RSAM, which stands for real-time seismic amplitude measurements, which is this blue line that you can see here. We correlate that with the electromechanical parameters of the generation units, such as the speed, which is this line here, and with the power delivered by those machines. So what you can see here is these peaks that are related with that first spin of the machines. And what we could analyze is that when the machine reaches its nominal speeds, which is 180 RPM, the seismic amplitude increases slightly. Here we also can see the frequencies associated to those tests. And it's important that you know that we continue monitoring not only for those tests, but in every moment, 24/7, and now in commercial operations, all of this, not only from the seismological part, but we try to correlate and to verify what is happening in the different workstations. So I think that would be the most important conclusions based on what we had previously shown you, and is that the operation of the plant is safe, and that the part of the project that is pending is monitored very rigorously. That I would say is our greatest responsibility, to be able to count with quality information and act proactively when necessary. So with this, I conclude my presentation. That is, in a very summary terms, what the TMC is about, and yeah, I hope you like it. I don't know, Danny, if you want to add something.
I think that's okay for us. Maybe Daniel, if I can go, if anybody has a question or a comment about it.
Yeah, thank you very much for the presentation. So now we have time for the question. If there is any question here in the room, let me know. If there is any question online, please raise the hand online. So any question in the room? Yeah, I have a couple. Okay, no. Victor Restrepo, can you unmute yourself, please?
Yes, thank you very much. It was a pleasure to see the presentation and all what you guys have been doing for gathering all these instruments and getting in a unique platform in order to visualize and analyze information. So congratulations for this. I believe for so far what I have seen before, it's one of the most complete dam that has the most advanced instrumentation, or so far what I have seen. So that's very good, and for Colombia projects. The question is regarding how difficult it was to gather all different technologies and vendors in one platform that I saw that it's pretty much a GIS platform. So how difficult it was to do this, and if it is a big challenge, if it was a big challenge, or in the process you find that it could be done easily for the different technologies you have found.
Yeah, Victor, thank you so much for your words. To answer your questions, I would say that it really has been a big challenge, and I have to comment that this work has had a lot of participants, not only personnel from EPM, but of course we have been working with personnel of our advisory, the constructor, the interventory, and part of our responsibilities has been to assess whether technologies or what technologies are useful for the project, and how to integrate that in one platform. We are still doing it because we have reached a lot, but we're still pending to configure another platform so we can integrate more and more information and to centralize everything just in one big database. So as you could observe in the presentation, we have different tools. I would say the main tool is ArcGIS Online because it is a powerful tool. But we also have another softwares and I mean a lot of providers, and we try to be very organized with that. But it's a process that started in 2018, and we are working on that. We are still working on that.
Yeah,
Okay.
thank you very much.
I guess next one is Colin.
Yeah, just wanted to say to Juan and Nestor, really wonderful, really impressive monitoring scheme, and the in-depth walkthrough that you guys took us through. That was really great to see all the different layers of it. I had a couple more general questions about the facility, if you'll allow me. The first one being, you showed a displacement plot. You presented it when you were just introducing the interferometer data, and you mentioned that it looked like the displacement was the rate was at a pretty good clip, and then it kind of tapered off. And you mentioned that there were some remedial measures that were imposed to slow those displacements. I'm wondering what those measures were, because it looked like they worked really well.
Colin, I'm sorry, can you repeat the question? And maybe if you want to go back to the presentation, you want to see any specific slide?
I didn't actually catch the slide number. I think it was when you were taking us a walkthrough of the interferometer data. It was just a question about the displacement plot that you showed. I'm not sure of the specific. Yeah, exactly. Yeah, that's the one. Yeah. So you can see the displacement. Obviously, you mentioned that the remediation that was done, or that there's remediation done, and obviously you can see from the plot that it seemed to have worked really well. So I was just wondering what if there's some background you can provide on that, what the remediation was.
For the corrective measures.
Yeah. Yeah. Exactly.
If you can explain, you have more detail about the treatment that was applied.
Oh, okay. I understand. Sorry, Colin. Okay, so the first thing we had, when we had this movement, we have here a geotechnical engineers team. So they start to, this is like a feedback of these displacements. And they put that in finite element models, so they can pretty much understand what are the ground conditions to produce those kind of displacements once you construct the model. So in order to do that, they started to design the like an additional support, especially in that part. For example, in the blue one, which is the more or the other part that had most part of the displacements we registered. So they started to design the stabilization, and actually there we had to use very long anchors, because we had like a very thick soil layer or soil part in that slope. We have a very steep slope, so they started to use this registration or in this displacement to put that in finite element models, and start to try the support, and they arrived to the answer to reinforce the slope with long anchors with cables, anchors, and shotcrete.
Okay, great. So this must be a really good example then of using I'm guessing I'm assuming there's a very comprehensive geological model of the site, and using your instrumentation data and also finite element to come up with obviously a very good solution. So interesting. Yeah, thank you.
Yes, sir. Thank you. It's a pretty much interesting exercise, because it's a continuous feedback.
Exactly. Yeah.
Also during the construction, you can check all the displacements and make adjustments like real time to your models and to your support designs.
Great. Thank you very much.
Welcome.
Does anybody has any question here or online? Because otherwise I go with my questions. Okay, so I will go with my questions. I have essentially two questions. Question number one is, as far as I know, that kind of, I mean, that dam is between those, I mean, those mountains are mainly metamorphic rocks, but you have a really thick weather soil over that metamorphic rock. I wonder if you were able to follow the pore pressure distribution mainly during the whole process and when the filling of the dam. And I'm asking this is to know if there is any relationship that you have seen in the behavior of that pore pressure in that weather soil with the displacement that you are recording all the time.
Thank you, Daniel, for your question. Yeah, we have piezometers in most part of or major part of the fronts. Talking about, for example, in the dam, we have a lot of piezometers at different levels, and we you know, when during the construction process of the dam, we check the piezometers, and also we measure the infiltration in the dam, for example, just to see how not only the soil part of the mountains or of the ground behaves, but also the rock. Because as you mentioned, we have metamorphic rocks, and they are most of them are pretty much fractured and you know meteorized. So yeah, it's a very interesting exercise because we follow all the pore pressure, and also I don't know if you mean, for example, not only in the dam but in the you know in the margins of the river while the reservoir was increasing its level. We also monitor in some important slopes with piezometers how the water level increased in the soil, and how that affected, for example, the slope stability in the margins of the river while the reservoir was increasing its level.
Maybe we didn't mention that in the presentation, but we also carry out infiltration measurements in all the body of the dam, in all the complementary galleries. And what we have seen is that those measures are low in comparison with other dams in the country. So that's really good news for us, and we are like we feel very safe with that measures.
Yeah, we, for example, I don't know, in this is like as I mentioned, this is a 20 million cubic meter dam, and infiltrations are less than 200 liters per second in the whole dam. So it's a pretty much low value for these infiltrations. And also we perform a willow stick test, which allows us to see what are the main paths for the infiltration. And what we saw is that infiltrations occur in the margins, in the rock mass around the dam, but not through the dam. So we can see how you know we are pretty much confident about the construction of the rockfill and the clay core of the dam.
Okay, perfect. Thank you very much for your time. I guess we don't have more time for questions, but I really appreciate the time you take for prepare this presentation and for being here sharing this project. And yeah, thank you very much everyone for being here.
Thank you very much, Daniel, and to the University of Alberta. We are very honored and proud for presenting our project, which for us is very important in Colombia. So thank you very much for your time.
Thanks, everyone.
Thank you.